from the observation of the empirical rule. People saw that there was, in fact, some tendency to cluster around the middle and progressively fewer observations in the tails. So this shape is actually very beautiful. At least I think it's very beautiful. It's aesthetically pleasing. And it also shows up everywhere. I know it sounds odd, but I mean it. It's like watching a sunset. It's like a circle or a straight line. It literally shows up in nature when you look at it. When you look at, well, mostly distributions on the net, but still, it just crops up pretty much everywhere. And it's a remarkably useful facet of nature as well. So we're going to spend quite a bit of time talking about the normal distribution, because not only does it seem to have some fundamental role in our existence, it is applied everywhere. It also gives us the basis for future work, because a lot of statistics are in fact normally distributed directly, or they are related to the normal distribution. We're going to talk about the T, the F, and possibly the chi-square later on, and all those are based on the normal distribution. Okay. In some ways, it's a very simple distribution, perfectly symmetrical, determined by two parameters exactly. There are a lot of distributions that are more than that, but not this one. Basically, the mean just tells you, where this distribution is, and the standard deviation gives you an idea of how squished it is. So smaller standard deviation, much more centered around the mean. A larger standard deviation, you get that sort of the tails tend to fill out, and it becomes much wider. So, in addition, the mean happens to be both the median and the mode as well, so it is an extra simple structure. There are a few facts about the probability mass. So within the standard deviation, you find 68.26%, 95.44% within 2, and 97.72% within 3 standard deviations of the mean, which of course is what?
Empirical?
What's that?
Is it not empirical?
The empirical rule, exactly. And in fact, the normal distribution is what gave rise to the empirical rule, right? You tend to observe things in nature that had more or less that distribution, and then what a gentleman by the name of Gauss, I must have mentioned Gauss, discovered was that there is a mathematical structure underlying these observations, and that, of course, is the normal distribution, which is also known as the Gaussian distribution. So when you're told that noise is Gaussian or something like that, that's what's meant. Here is the functional form for the density function. And it's, for some reason I have trouble memorizing that. But it doesn't matter, because it turns out that finding the area through calculus is impossible. It's literally not something that you can do using calculus. And that is a theorem. It is a theorem that you can't do something, which is quite unusual. It turns out that when you do it, or when you try to do it, you end up with an infinite nested set of intervals. So you must calculate the areas under the curve of a normal distribution with numerical methods. And you can get arbitrarily close, but you're not going to find that limit. That makes it actually easier for us. Because if you open up your text to the inside front cover, you will find a table of the cumulative density function for the normal distribution. And of course, our beloved authors have decided to innovate. So the 10th edition has changed that table from what exists in the 9th edition, where the 9th edition has the version that is more or less not just widespread, but universally accepted. We'll talk about both of those tables, however. Okay. So, in order to calculate anything based on the normal distribution, we have to translate into one particular type. And here's the thinking. let's say we have some normal distribution with a mean of mu. Okay, and this is written distributed. That's what the tilde or squiggly means. Squiggly being the technical term. Normally, the mean of mu is standard deviation of sigma. Okay? If you want, we can specify that mu is 100 and sigma is 10. Now, let us say that we're interested in the probability that x is less than c. Well, just like with the uniform, we indicate that with area. And immediately you can tell me what about the probability. Greater than 50%. Excellent. Because the probability that x is less than mu is 50%, so we add this piece, and you have to have some number larger than 50%. So if we're interested in this statement, it's perfectly legitimate to subtract a number from each side of an inequality, right? Anybody protest vigorously or otherwise? No? All right, so this is equivalent to this statement, right? And it turns out, this here I expect perhaps slightly more protests, that this is true. Okay, if there are no protests, my question is, why is it legitimate to divide by sigma? There are at least two, there are precisely two things you have to be very careful with.
The sigma is positive, so you can multiply on both sides without any change in the greater than less than thing.
That's exactly right. Sigma is positive, so you don't have to change the direction of the inequality, right? But in addition, since sigma is positive, it is most specifically not equal to 0, which would be bad. So this statement is equivalent to this statement, and we denote this as z. Now, that's by definition. But it also makes perfect sense in the sense that we've used before, z being the number of standard deviations away from the mean. X minus the mean divided by the standard deviation gives you the number of standard deviations away from the mean that you're interested in. However, and this is sometimes used slightly confusingly because quite often this number is just labeled z. However, my point is this. If this statement is true, then this statement is true. And so therefore, the probability that x is less than c is equal to the probability that z is less than c minus mu over sigma. Right? Because these two events are identical. If this is true, then this is true. Yes? Any questions on that? Now, I haven't shown you that z is in fact normally distributed, but it is. In fact, it's the simplest possible normal distribution. So what's the simplest possible mean that you can imagine?
0.
0. Very good. So a perfectly symmetrical distribution now, it's symmetrical around 0, which means that if you're interested in negative numbers now, you don't have to adjust for the mean to get positive, you just simply remove the minus sign, or add one. What's the simplest possible standard deviation to work with?
1.
1. And it's not 0 because?
Well, then it would have no width.
Okay.
Exactly. If sigma was 0, you'd be dealing with a constant rather than a probability distribution. Okay, good. Now, what we end up doing is translating. So, So instead of looking up x less than c, we looked up z less than c minus mu over sigma. Why? What have we gained by this? Except, of course, for the fun and games of messing around with algebra.
We know all the values
Of
we know if you have a distribution, we know the mean and sigma,
yes, we do.
and then c is the value you want to get less than.
Very true. So we can calculate this. But do you have any idea why we're bothering to do it? Why we're calculating it?
Find probability.
Find the probability. That's right. So what are we missing from that chain of logic? If you think back to the uniform distribution, at this stage, we would simply have taken width times height, right? Find the probability. But it's kind of hard to take an infinite width times something to give us a number. How do we do it? Any ideas? Very good. Use the table. However, that means that you know the answer as to why we went through this exercise. No? Is it obvious to everyone? Is that why we're having trouble getting past this step? Or is it not? I'm gonna guess not.
Yeah, that's the one.
So let me ask you this. If we wanted to have tables for this distribution, right? With mu equal to 100 and sigma equal to 10. Well, let's just fix sigma equal to 10. How many possible distributions do we have just varying mu?
Infinite.
An infinite number. And if we also vary sigma,
Infinite squared.
there you go. So basically you'd end up having papers everywhere, all of them comprised of a table of normally distributed random variables. Incredibly impractical, yes? But we've just shown that we can transform that into a probability for z, a normal distribution with mean of 0 and a standard deviation of 1. That is the one single table you need and the one single table that is in your text. So, I think we have an example, and we'll illustrate how this works using that example. So the idea here is that you're managing inventory, and every single time you hit 20 gallons left of this popular multi-grade motor oil, you reorder. Okay? There is an uncertain amount of demand in the time it takes you to get your order. You know, there could be an uncertainty in the amount of time you actually get the order. It could be uncertainty in the amount you're given. It can be uncertainty simply in the number of customers that show up, and it can be uncertainty in the quantity they order. So I don't think it takes a leap of imagination to accept the idea that there is some distribution for the amount of oil demanded during the period after you've reordered, but before you get your order, right? So here's the situation. Here's 20. This is time. Here's oil. And you know, your stock might vary a little, and then boom. Here you reorder. That's this reorder point. And then you move up, get another order. So this is where you get the new order. And then you start the whole process again. And then every once in a while you go under. Now, when you go under, you've got a problem. Right? You have stock out. So you have customers showing up that you can't help. What we're interested in here is the distribution of the amount of demand. In other words, this distance. And that we are told to assume is normally distributed with a mean of 15 and a standard deviation of 6. So, can you come up with some critique for that? It is an approximation, so there are at least 2 ways you could criticize this. Probably more. If you don't want to criticize it, let's praise it. How does a normal distribution suit our purpose, you think? Like, for instance, what this is saying is that basically the bulk of the distribution of the amount you need to get up to 20 here is centered around 15, right? You're going to have a lot more observations just above 15, just below 15 than you are going to get observations way out here in the tails. Does that make sense? I mean, typically you get, you get a certain, you're probably not going to get an immense number of orders. You're certainly not going to get 2 clusters if you have a large number of customers coming in, because customers tend to average each other out. And so you get a fairly uniform type of, unless, I mean, you could have some immense customers that just throw everything off. But in terms of criticism, you've got the continuity argument. To some extent, you don't know if you're actually selling oil in discrete blocks or not. You don't know if remember, the distribution goes from minus infinity to plus infinity. So it's rather unlikely that you're going to get more oil returned to you than you ever sold in the history of your store. But according to this, there is some positive probability of that happening. So there are some small weaknesses. Okay. What we're first asked, though, is what is the probability of stockout? So stockout means what?
In less than 0.
Okay, one more time, the one at a time.
Highest demand?
Well, we need a little bit more specificity.
Your inventory goes to 0.
Your inventory goes to 0, right? Okay. Since you order when you have 20 gallons left, that means your demand has to be
Greater than 20.
very good. So as long as you have a demand of 20 or more, then you've got stock out. Let's calculate the probability of that. Well, first of all, since the mean is 15, 20 is going to be somewhere around here. And so the probability of stock out will be represented by which area? Very good. And based on this fabulous drawing, you can immediately tell me something about the probability.
It's not greater than
You can probably,
Less than 50.
it's less than 50%. Okay, I'm gonna have to remove some of this.
Roughly 15%.
Okay, any ideas as to our next step? Based on our previous conversation?
Calculate probability less than 20,
Okay,
less than or equal.
okay. But remember, the probability that x is less than or equal to 20 is equal to the probability that,
X is less than 20.
right. So we're not terribly worried about that aspect.
Convert it
Probably
to
one
the
a Z somewhere in here.
There you go. Okay, so we want to translate this. So we have, well, can you tell me, just looking at it, how many standard deviations above 15 is 20?
Less than 1.
A little less than 1.
Right. So standard deviation is 6, we're at 20. So we've got 20 minus 15 over 6, which is 5/6, or roughly 0.83. Yes? All right, now this is where our different tables come in. So first of all, the traditional style table gives you the area between 0 and Z under the curve. So if we look up 0.83, and by the way, the first digit and the first decimal is in the left-hand column here. The second decimal is represented by the topmost row. So when we look for 0.83, we find 0.83. And we note that the number given, the area given is 0.2967, which is this area. Questions on that? Okay. Anybody have the February or 10th edition? Thanks. So you'll notice the 10th edition, well, doesn't do much at all. There we go. It actually gives you the full cumulative probability and goes from -3, actually -3.09, and all the way up to +3.09. But basically it takes 2 pages to do what the 9th edition does in 1 page. So we're not exactly going to get the answer from this page, although I suppose we could. When we look at it here, .83 is right there, 0.7967. But notice that we're seeing something different, right? We're seeing everything to the left of .083. So, to compare, this half has to be 0.5, and so together these pieces are 0.7967, which of course is what you see in the 10th edition. Any questions on that? I'm going to provide you with a table for that's similar to the one in the 9th, but if you prefer the one in the 10th, you're welcome to photocopy it and bring it with you to the fund. I have no problem with that.
Well, for that answer there,
But we act,
aren't you taking 1 minus what we just looked up in the table?
Very good. We're definitely not quite done yet. So, we want this probability. So there are a couple of ways we can do it. We can take 1 and subtract the 0.7967, or we can take 0.5 and subtract just this piece, right? Any questions on that?
So if we're using the 10th edition tables, you're just saying 1 minus that factor that's in the table.
Right, it'd be 1 minus 0.7967, which is the same, gives you the same answer. Other questions? Yes.
Which ones are you going to provide them? Which ones you're going to provide
The 9th edition version.
for final?
Yeah. It doesn't, you'll be able to read either one. If you're able to read one, you really can read the other. The key is going to be to draw it. But that's why I also said, if you really don't want to, feel free to make yourself a photocopy.
Oh.
Other questions? Okay. other logical question to ask you, if you're managing this process. Remember, this is what you found, there's a 20% probability for stock out in any given month, or any given period.
How long does it take for a shipment to come in?
True.
When you reorder?
That's true. Might be possible to speed that up. But if you
What
don't
are-
have control over that,
Maybe what's my expected loss?
what's your expected loss? Excellent. And there are two components to that, right? Which one of them?
Well, there's, I guess, opportunity cost. If you're handling too much, you don't wanna have too much surplus all the time. That would be one.
Okay, so there's a cost of inventory,
Mhm.
good, and there's another type of cost.
Lost sales.
What's that?
The cost of your lost sales.
Yeah, that's true too, and, so sorry, there are at least three types. Basically, the idea is you need to enumerate all your types of costs, right? And then you minimize the types of costs. If you show up a place and you've been guaranteed oil and they don't provide you with oil, then you're typically not entirely happy with them and perhaps less likely to
Cost
go
of
back,
lost business.
more likely to cuss at them. Maybe not, I don't know. But certainly express your displeasure in some way. And typically, the people at the store don't like to turn customers away. So there is a cost of,
Losing business.
there's a cost of losing business, and
Compensation for,
there could be a compensation cost. Usually you just lump all that together under stock out costs, right? So there's a cost of holding too much, and there's a cost of holding too little. And because there's a random element, you're not gonna get rid of these costs. Both of them are gonna have a positive probability of occurring in any given month. So, let's assume that the manager has decided that 20% is just way too much to live with. And there's no way for you to pick a probability based on the information we have, but the manager chooses 5%. He thinks 5% is decent. How do we figure out, well, let me ask you this. What would we use the 5% to accomplish with this structure? What would we change?
Change the reorder point.
Change the reorder point. Excellent. And can you say anything about the direction of change?
It's gonna be a bigger number, so you're gonna be looking for 95% on the chart.
Very good. Very good. So we're going to try to change that, and it's going to be some increase in order to force the stock out probability to be 5%. So, excuse me, what we know now, is it clear to everyone that we're gonna have the stock out on the right, item in? Okay. So this piece here is 5%. What's the next step? Maybe I should label, this is what we're gonna look for, why?
Calculate the table value associated with that.
Okay? What do you find?
I don't have that table,
Ah,
but you could.
then it would be kind of miraculous if you found anything. But let me provide you with the table, and you can tell me what you found. If you can read that, of course. What are you looking at?
0.0199.
Go with, 2.57. The sigma value we're looking for.
Okay, tell me your logic, what are you thinking?
That if we want 5%, then I want the sigma value that's associated with 95, and so 2.57 gives me a sigma value of 0.495 approximately.
495. When you say sigma value, what is, what do you?
Or a Z value.
Okay, 495.
Right.
Okay. So
I don't want that.
basically
I
you're
want
saying 0.5 minus point, yeah, 0.5 minus 0.495 is
Yeah.
not 5%, that's 0.5%.
Yeah.
You're on the right track though, but let me illustrate for everyone what the thinking is here. So it doesn't matter if you're doing this in terms of X or Z, if you want the tail to be 5%, how big is this area?
50,
That's the
45.
45%, right? Now, you have to read the table backwards from what we just did, yes?
1.64.
Okay, good. And how did, so you found the number closest to 0.45, right?
Right.
Okay, and in fact, it's quite right, 1.6. So these two numbers are the closest you're gonna get, yes? When you follow that up, you found that, wait,
0.4495.
644.
there we go. Those two numbers are the closest. So it's some number between 1.64 and 1.65. Yes? Anybody not, well, raise your hands, those of you who saw that, or followed that. Okay, so there are a few questions left. What we're trying to do, one more time, is we want to ensure stock got to be 5%. In order to figure that out from the table, we find that that means this area has to be 45%. That's something we can look up in the body of the table, because that's what the table gives us. We find the closest we can get to 45% is represented by these two numbers here. And so if you follow that all the way to the left, you get 1.6, and follow these two up and you get 1.64 and 1.65. And it turns out that the actual, you can't usually interpolate, but the actual cutoff is 1.645. So the Z is 1.645, but recall what the Z is telling you. What does Z measure? It is the number of, yes,
Standard deviation
from
from the mean.
the mean. So we're 1.645, standard deviations above 15. Does that tell us enough to find y? Yes, and if you wanted more from a definitional point of view, x minus mu over sigma is equal to z, and that's exactly the same thing as x is equal to mu plus z sigma. But now we know mu, we always knew sigma, and we found the z of interest, so this is 15 plus 1.645 standard deviations of 6, and that is equal to 24.87, which we note is greater than 20 and more or less in accord with what we expected. Yes? So those are really the two approaches to calculating normal probabilities. You start with some number along the real number line and find a probability, or you start with a probability and find some number along the real number line. The classic error that gets made when you first start working probability, normal probability problems, is of confusing area with number along the real number line. So I've seen people take 0.45 minus 15, for instance, and that's worse than wrong. That actually indicates a fundamental non-understanding. So that's bad. Any questions on what we've just done? Okay.
What is that 24.87? Say
It tells us that once the level of your oil stock reaches 24.87, you replenish. And if you follow that rule, then you only have a 5% probability of stock out. So I'm guessing most people would round up to 25 and reorder them. So this is how you again find the table and find that answer. Okay, so let's do a problem with the normal as well. Even though we've done an example, it's fully visual. Okay, so this is problem 41. And here we have a quality control problem. Motorola has decided that we can use the normal distribution to determine the probability of defects with a process that makes items with a mean weight of 10 ounces and a standard deviation initially of 0.15, where a defect is something that is one standard deviation away from the mean or more. So you get this situation. Just imagine a machine that is set to produce at exactly 10 ounces, but of course no machine is perfect. Initially, we have a standard deviation of 0.15 ounces, and in fact, we know that we have a normal distribution. Right now with this standard deviation. So, one standard deviation above the mean is 10.15, one standard deviation below is 9.85. And so, what area should I shade in to indicate the probability of defects?
Yeah, right outside.
Less than 985.
Exactly. Right? Now, how do we find the probability of a defect? Excellent. Excellent. Okay, so I found that I got a lot of good suggestions, and I think if we put them all together, we pretty much have the answer. So we're done. Okay. So the first thing we're going to do is translate. But we already know that this is placed one standard deviation above the mean, so we know this is 1. We don't really need to calculate that. And as was pointed out, what is the relationship between these two areas?
Equal.
They're equal, so you really don't need to do this twice. You can simply recognize that the probability of a defect is 2 times the probability that x is greater than 10.15, which is the same thing. It's 2 times the probability that z is greater than 1. But of course, if you look up 1 in your table, what do you find?
480.
I really meant the number in this particular case. What's that?
0.84, 13.
Okay. So this would be the 10th edition version, and here, if you look up a z of 1, you find 0.8414.
1.3.
1.3.
Okay, 1.3. Okay. So given that, very good. So that's 2 times 1 minus 0.8413, or 2 times 0.1587, which is 0.3174. Everybody agree with that? What's that? 31%. Yes, 31.74%. Very good. Now, let's say we do this 1,000 times in a row. It's a 1,000 run production unit, so to speak. what is the expected number of defects if you have independent runs?
317.
Very good, so the expected number of defects Okay. You're doing this 1,000 times. Each trial is independent. The probability of defect is the same each time. And you're interested in the number of defects. What structure are we talking about? I'm sorry? Okay, we're doing this 1,000 times. We have independent productions of each unit. The probability that each unit is a defect is the same each time. Very good. Binomial. Yes? Everybody see that? So this is a typical application in statistics where you start out with one structure, a normal distribution problem, but then in order to apply it to a sort of a larger problem, you note that, well, this will fit a different structure. Start with the normal, go to the binomial. It's also considered a rather more challenging type of problem because once you get to that stage, you're thinking normally distributed, right? That's sort of that's your mode. Sorry, I shouldn't use that word. That's your way of thinking. And we really want to move, we really want you to be able to recognize when to use any type of tool, right? Use whatever is most appropriate. And that is perfectly, it is perfectly appropriate to use the binomial in this context. And in fact, what we've done here is we've taken the number of trials, n, times the probability of, well, success, p, and found the mean. Okay, that's rather large. Motorola was not terribly happy about it. So, the solution was, or part of the solution is to drive down the standard deviation. Instead of a standard deviation of 0.15 ounces, they discovered they were able to drive it down to 0.05 ounces. But they left the control limits in place. It turned out that anything less than, or anything within 9.85 and 10.15 was acceptable. And it was only outside of that that it mattered that you were deviating from 10. And so a defect was still any number less than 9.85 or more than 10.15. What is now the probability of getting a defect? At the very least, you can give me a bound to it, right? Is it going to be greater than or less than 31.74%?
Plus that.
Less than. Okay, so remember the first thing we did was translate to a z. What is the z-score for this cutoff?
3 deviations.
How'd you get that?
Because the new deviation was 0.05,
Mm-hmm.
and we're 3 times that.
Right, and we're 0.15 away from the mean, so that's 3 standard deviations. We write it out. You see that that's 3, and this is minus 3. But other than that, the logic is identical, yes? So now the probability of defect is still 2 times 1 minus the probability that z is less than 3. So that's 2 times 1 minus what?
0.9986.
That sounds right. 0.9. what'd you say, 8.6?
Yeah.
8.6? Yeah, so it's ingredient. 2 times 0.0014 or 0.0028. So you notice the probability has plummeted. And in addition, therefore, the probability of, the expected number of defects has plummeted as well. What is the new expected number of defects?
Less than one?
Mm,
No,
Well,
it's,
1,000
yeah.
times
2.8.
0.0028 is 2.8. And just as a review, well, actually, before we get there, questions on that? So does it seem advantageous to run a tighter production process, bring down the standard deviation? Clearly not losing as much to defects, right? So, just for fun, what is the probability of getting exactly 3 defects in the new situation?
0.
How do you get that?
Never mind.
That number.
That's true, but remember what I was asking. What is the probability of getting exactly 3 defects in the next production run? It is an exact number, but is that a problem? No, you're on the wrong track here.
So at least, you go 1 minus that, it's exactly, so it's less than 3 or greater than 3.
Lost. It's less than or equal.
Welcome to the club.
That's always my agreement, to join the club. So we're talking about, okay, the reason that you're, I didn't realize it was quite that good, but I'll have to remember that. The probability that we have exactly 3 defects in the next production run, you're telling me the probability is 0 because it's an exact number. Okay, but am I really talking about a continuously distributed random variable here?
Defects are units,
Discrete.
it's not
No.
continuous.
Because they're independent?
No,
Because-
the answer is no, but it's not because they, whatever they are, independent. It is,
Discrete.
yes, that's excellent, the opposite of continuous, indeed, well done. And in fact, in particular, the number of defects is distributed, I keep looking this way because the right answer came from there just a moment ago.
Binomially.
Binomial, very good. You have a certain number of trials, each trial is independent. You have 2 outcomes, right, success or failure. The probability of success is the same in each trial, and you're interested in the number of successes. Of course, in this case, the success is by definition a defect, but that's okay. So, again, how do we find the probability of getting exactly 3 defects in the next production run?
Probability of 1, probability of 2, no.
Cube the,
What's that?
you cube the, probability,
Of,
0.0028.
well, okay, let's think about what that gives us. That gives us the probability of getting 1 defect in the first, okay, a defect in the second, and a defect in the third. So that would be the probability of getting 3 defects in a row.
1,000 choose 3.
Yeah, it'd be 1,000. It'd be a binomial function.
It would.
choose three, the probability, what's the probability again? 0.0028.
We'll just call that little p.
Little p to the third,
To the third, yeah.
1 minus p to the 1,000 minus 3.
There you go.
That wasn't fun. You said just for fun, and you, that was.
Yes, but you're missing a key point there. Who is it fun for? It'll be fun by the time we get done with it. I'm busy brainwashing it. It'll be fun. So what are we doing here? What does this piece tell you?
Not successes, I
Yeah,
mean,
it's the
failures.
probability of failure.
Oh, sorry, my stance is not wide enough. I actually meant this piece here.
That you're choosing for the three, and then you're subtracting the probability of one. Well, the probability of each choice, you're subtracting it from one.
So exactly,
Something like that.
exactly 3 successes and 3 failures. No, 1,000 minus 3 is 997 failures.
There you go.
Yeah.
Remember last time when I was writing down the long list of possible sample points, right? I'm not doing that with 1,000. But remember we had 10 different outcomes. First we had all heads, then we had mostly heads, but 1 tail, right? Then we started on 2 tails, yes? And so on. Here, we've got 3 failures and 997 successes. Or the other way around, doesn't really matter. So what we would end up doing is writing down an enormous list of sample points. But every single time we had a particular sample point that had 3 defects, we could find the probability of observing that sample point. That particular sample point, for instance, with 3 defects at first and then 997 failures. And what would be that probability? What would be the probability of seeing exactly defect, well, failure, all the way up to the top. So we've got 997 of them. What's the probability of seeing that in that order?
Choose 3, right?
1,000 choose 3 is a very big number. Probability's got to be a number between 0 and 1.
So, I mean, 3 divided by 1,000, no.
That's too easy.
No.
That's no fun at all.
Yeah,
1 over
What's that?
1,000, choose 3.
You're saying the order matters, is that what you said?
All I'm saying is I want the probability of that particular sample point where the D's show up in the first 3 rather than at the end or anywhere else.
Very slim. It would be,
Very slim, but that's technical. But think about this. What is the key point of independence here? What does independence give us? Okay,
multiplication.
multiplication, very good. So this is equal to the probability of a defect, times the probability of a defect, times the probability of a defect, times the probability of a failure, times the probability of a failure, and this is 997 times, right? Now, any one of these P of D's is a little p, and how many of those do we have? 3, so that's the same thing as p to the third, right? There are 997 of these, so that's 1 minus p to the 997, which should be familiar,
yeah.
yes? Now, we can place those 3 d's over here, we can spread them out, We do all sorts of things. The key question is, how many ways can we write down 1,000, I'm sorry, how many ways can we write down these thousands positions where 3 of them happen to be Ds? But we don't care, we're not distinguishing between the Ds, right? They're all equally valuable. Members of the defect family. 10 choose 3. There are 1,000 choose 3 way of writing, ways of finding sample points where there are precisely 3 defects. So that's why we get the second part. Multiply by the number of sample points with this, where your type had 3 defects, and the probability of any one of those sample points showing up, and you get the total probability of 3 defects. Alright, we're going to actually calculate this, because I want to make sure that we're happy doing so. Well, happy might be a bit ambitious.
Right, you can stop right now.
What's the probability?
No, the probability we're happy doing.
The problem, well, that's not what the point is. Okay, the 997 factorial, so that long tail, that cancels out, right? So we just end up with 3 times 2 here, and then we have 0.0028 to the power of 3, and we have 0.996, no, I'm sorry, not 86, 996, no, 7.
7, 2.
There we go. To the power of 997. Now, well, we can cancel a few things out. This becomes 500. This becomes 333. What you'll find is your calculator will have trouble with this if you just plug it in. And which part do you think causes trouble? Actually, try it. Or we can all try it, I suppose. Let's see. Oh yes, this is where they hide the calculator.
Yeah, 3 down from there.
There we go.
You use the right kind of calculator.
What's that?
Use the right calculator.
Yes. Okay, so this is, so see, that's not a terrible number, right? 6%, 0.061. Approximately. However, if we tried this middle one, 0.0028, oops, that's not right.
Very small.
That's a very small number. And what you'll find is that if you multiply, depending on the calculator, I think this one actually can do a decent job of it, but because it's keeping quite a few decimals. But I've seen a lot of calculators tend to round off about there, in which case you lose a lot of detail. So I'm going to leave this one, and we can see if this is going to work. Let's see, 500. So that's a very big number, and when we multiply those two numbers together, so that's 1. All right. And that seems to have worked okay. And then should have kept this in memory. Well, I clearly did something wrong there. Okay. Oh, yeah, okay, let's try this again. 500 times 3 times 998. And then I'm gonna just multiply by okay, and then we're finally also going to multiply by 0.972, because clearly you're not gonna do that 997 times. There we go. Approximately 0.22. So there's a 22% probability that you're gonna get precisely 3 defects in 1,000 tries. So I thought it was a rather large number, actually. Any questions on how to calculate that? On the normal in general? At this point, you actually look like you really, really want a break, so let's take another